Hello everyone, and welcome to our first lecture for our second unit of the year, which is going to be on the topic of biochemistry, which I've said before really is going to be focused on some of the key macromolecules such as carbohydrates and proteins that we eat in our daily diet. And as you can see from the picture, you know that we have all eaten a little bit questionably over our lives, correct? No matter if it's 50 hot dogs, dog food, cat food, we've all made mistakes, and we continue to make mistakes in what we eat on a daily basis. So hopefully this unit will give us a little bit more leeway into having a better judgment from this point forward. So let's begin our unit. With the idea of this unit, and at least this first lecture, is to try to explain the role of carbon and hydrogen in living things. All right, what's carbon's ultimate purpose? As well as we'll start to introduce the idea of what we call polymerization, which is a process in which we create larger organic molecules, and we have this huge diverse options for them and what we can create using carbon. So we can begin with what is an organic compound. All right, so no matter how small or large it is, an organic compound at least has to have two specific elements, and those elements are going to be carbon and hydrogen. It does not matter what else is present. A molecule cannot be considered organic, meaning that it's really used in living things, unless it has at least carbon and hydrogen. Will you find other elements present? Sure. Like in this diagram here, every little black ball would represent a carbon atom. And again, what we're going to learn is carbon really is the backbone or the spine of every large macromolecule, no matter what it is. And then hydrogen is really the most useful because it kind of fills in all the little spots where we have an electron demand. And then what we will also see a lot of times is we will see oxygen present, which is the red balls there on this space defining model. But again, anything from this point forward that we're going to call organic has to have at least carbon and hydrogen present. Now, again, refocusing on carbon, all right, it is used to create this diverse amount of organic molecules that we have, all because of its key properties that we already introduced in last unit. So first off, carbon can bind pretty much with almost anything else on the periodic table. And the reason for that is it only has 4 valence electrons in its outer energy shell. So if you come over here and you look at, all right, the second energy level, again, no matter if it's Lewis dot or if it's our energy level configurations, it needs 4 more electrons to become stable, but it also has 4 more to give in order to get those 4, something that most elements do not have. So it is going to be able to form up to 4 other stable covalent bonds as a result of that. On top of being able to form 4 covalent bonds with 4 potentially different elements, it can also bind with itself. So you can take 2 carbon atoms and bind them together and create a single bond where each carbon's only sharing 1 electron apiece, or those 2 carbons could share 2 electrons and form a double bond with each other. So this will be an even stronger bond between 2 carbons. Or top that off, and you could even do a triple bond between 2 carbons, where they're sharing 3 pairs of electrons between each of the 2 carbons. That is an extremely strong and stable bond. Visually speaking, this is how it would look. All right, so first we start with ethane here, which is C2H6. This would be the single bond. Remember what a line represents? We discussed this last unit. Pretty much it means that you are just giving 1 electron for 1 electron, all right, to make a pair. If I start to form more bonds between carbons, my hydrogen need is reduced. So in ethene, you have 2 double bonds between carbons, all right, or in ethyne, you have 3 triple bonds between carbons. Extremely, extremely stable. Now, why can you not have a quadruple bond? Is it impossible? No. It's just highly unlikely and highly unstable. The reason being, if I bring your attention down here to this picture, can you see how the bonds start to flex below? And you have 2 of the 3 bonds kind of bowing outwards. That's because, remember, all these little lines here are representing electrons. So you have electron pairs that are all in these bonds, and electrons or negative charges will repel each other. So a fourth bond gets bent out so much that it usually just breaks as a result. So generally, we only really find in nature, most times, triple bonds, and then any other electrons that are needed are filled in by other elements. Now, when you find almost pure carbon, so the majority of the bonds between carbon are triple bonds, that's what diamonds are over here. All right, they're pretty much almost pure carbon. If you start to, let's say, break a bond or a triple bond here and there, and you drop down to a double bond between carbons occasionally in diamonds, you can start to plug in other elements to meet the electron demand. Mn stands for manganese, and other elements, manganese or sulfur perhaps, you start to create impurities in the diamond. However, some people prefer that because when you add other elements, you can create colors or different hues within the diamond itself, which sometimes can be extremely rare because, for example, this one right here is called a blood diamond, right? And a blood diamond is contaminated with elements like manganese. However, it is so rare, it ends up actually being worth more money. But most times people are preferring to go with a good old clearest cut diamond that they can find. All right, so let's move on. Building organic molecules and polymerization. All right, in our next video, we'll discuss the two specific reactions and what they're called and how we can build as well as break down these reactions. So right now, we're just going to do an overall, just kind of like brief introduction. So polymerization is a process where you're going to take smaller subunits of a specific type of macromolecule and link them together to make a much larger one. So if you bring your attention over here to our little Legos, all right, let's say if I link all those Legos together, I'm going to create a larger polymer, all right, which has many monomer units linked together. Right now in their individual state, we would call them monomers. Kind of think of them as bricks. Put the bricks together, you can make a house. So these larger molecules can be anywhere up to a few dozen or even hundreds and hundreds of atoms, all right, all linked together to form these gigantic molecules. They're going to vary greatly in size, as I just mentioned, a couple dozen to a couple hundred. And as a result of this and all the potential that you can link them together, all right, whatever shapes that you create, for example, proteins, you can build them in any which direction and they can take on numerous different possible shapes. All right, the shape of what they form, all right, and how you put those monomers together is ultimately going to dictate the function. And hopefully you remember me mentioning that last unit, that shape dictates function, because it does. All right, so if you look at these two cute lines here, all right, the male and the female, think about the hormones that make them either male or female, as well as you. Testosterone is the main hormone found in males that gives the male characteristics, and estrogen is the main female hormone that gives a female their characteristics. Now, both of these, the chemical formula would be exactly the same if I were to write it out. But the way the atoms are put together, if you take a look at the structures right now, you can see that there are slight differences between estrogen and testosterone. For example, estrogen has a CH3 group right here, while testosterone does not. Testosterone is going to have some hydrogens bound to these points. These points here would be carbons. These are like shorthand diagrams, while estrogen does not. Estrogen has a double bond to an oxygen here. Testosterone has an OH group. However, the formulas are exactly the same. So just putting the atoms together differently ultimately changes what the function of this particular molecule is going to be. And this is what we call isomers. All right, an isomer, as I just mentioned, is going to be something that has the exact same chemical formula, but the structure of it is different, and as a result, the function is going to change. All right, so again, what you need to take from this is just small, tiny changes in the structure can have ultimately big impacts on what the function of a molecule or macromolecule is going to be within a cell. All right, so to kind of finish this up and try to think it through in our heads, All right, we're going to be talking about making large molecules or polymers during this unit. They're going to be made up of monomers, smaller subunits, which you can link together here in a polymerization reaction to create polymers. Again, polymers are going to be generally 3 or more monomers linked together. And you can just keep linking different monomer units together to form a larger and larger polymer. And don't forget, each monomer isn't just one atom. It could be something like C6H12O6, glucose, where you have dozens of atoms linked together. And then on top of it, how do you put those atoms or monomers together? Do you alternate the subunits? Do you do something like glucose followed by fructose, and then glucose, fructose, glucose, fructose? Do you just randomly put them together? You know, a glucose, fructose, and a couple glucoses. Do you do it in blocks, where you do several glucoses and then several fructoses and then begin repeating? Or do you take multiple different polymers? So imagine each little strand originally was its own polymer, but now you start to link them together and have this gigantic branching macromolecule. The possibilities are limitless, and if you literally just change one or two of the monomer units, so if the pointing right here to the block copolymer, let's say that right here where my mouse is, I change out that little monomer for one of the lighter ones here. Well, believe it or not, that could change overall what the shape of this molecule is going to fold into, and the function as a result will change as well. All right, so next video we'll talk about the 2 specific reactions that we use to either build or break down polymers. Thank you very much.